Hello everyone, today's topic is an introduction to eigenvectors and eigenvalues, material from 5.1. So full disclosure, this is actually my favorite chapter of the book, my favorite topic of linear algebra. So let me give this kind of some background here. So the idea behind these things called eigenvectors, eigenvalues is you want to choose, or let's say find, a basis for Rn that, let's say, works well, I'll explain what I mean later, for a given, well, this will always be a square matrix, let's say A. So we've seen that there's lots of different bases for Rn, right? We get one for any invertible matrix, and we'll see that we want one that somehow fits or works well with the matrix A. Let me give you an example of this. So if A is this small 2 by 2 matrix here, and let me take a vector that's, let's say, 2, 1, and another vector u, let's say, is minus 1, 1. Then what I want to consider is, let's compute what A times V is. So we know it's going to be another vector in R2 because this is a 2 by 2 matrix. It eats vectors in R2, spits them out in R2. So let's see, the first entry is 6 minus 2, which is 4, and then the last one is 2. And notice something kind of nice happens here, that when I multiply the matrix A times this vector, I get a new vector, but it's actually just twice what I started with. So again, so AV is actually just, let's say just stretches V by a factor of 2. So I can try to draw this, in fact, right? So let me try to draw a little picture here. So I started with 2, 1, so something like this. This was V, right? And then when I take A times V, it's in the line determined by that, that vector V. If I think of V as determining this line through the plane, then I started with V, right, this vector here, and AV was just a multiple of it. So let me just contrast that with the other vector. If I take A times U, well, that's going to be 3, 1, minus 2, 0, times the vector minus 1, 1. So in this case, I get, let's see, minus 5, minus 1, which is not now something times minus 1 run, right? This is not a multiple of what I started with. So in this case, I started with something like, so minus 1, 1 is something over here. And when I apply the matrix to it, I get minus 5, 1, which is, minus 5, minus 1, which is something over here. This is not now, so this was U, this was A times U. The resulting vector is no longer in this line determined by U. Okay, so I started with U, apply the transformation, I get something not in the line. That's different than this situation where I started with V and I got something in the line. Okay, so that's going to be kind of our definition here. So main definition of the day is the following definition. An eigenvector of an n by n matrix, well, it'll be one where the vector stays in that line. So it's a non-zero vector, that's important. V satisfying. Okay, so what should happen? Well, again, when I take A times V, I should get almost V back. It should be a multiple of V. So for some real number, this is lambda that we usually use. This is the tradition, is that you use this Greek letter, lowercase lambda. You started with a vector, and I multiplied it by A, and what I got was just a multiple of that vector. Okay, so lambda is called an eigenvalue. Okay, so the vector, eigenvector, is the vector where this happens. The value that you get, right, this stretching factor is called the eigenvalue. And let me just say, if AV equals lambda V, we say that V is an eigenvector, for A, eigenvector with eigenvalue lambda. So eigen, I think it's a German word. It means maybe like belonging to, or, So this eigenvector is kind of, it's something that's special to that matrix A. And let me just kind of, let's warm up with an example here. So this is kind of a typical story in linear algebra. If I give you, say, a vector A, and I want to know, is the vector U, let's say, 3 minus 2, is this an eigenvector for the matrix A? Okay, so what I was going to say is that this is a typical situation. I've given you a matrix, I've given you a vector, and I want to know, is this an eigenvector, right? So this is something where you just compute. This is another one of these examples where you just compute. What I do is I look at A times U, so this is 1, 6, 5, 2, right, times the vector you gave me. And what I get here is this is minus 9, 11. So notice now that this is not going to be a multiple of what you gave me. So this is no, since minus 9, 11 is not a multiple of U, which was 3 minus 2. What I got out of this process of multiplying the matrix times the vector was not a multiple. Okay, well, what about, so the next guy in the street gives you this vector, 6 minus 5. Is this an eigenvector for the matrix A? Again, let's compute. We take A times V. This is 1, 6, 5, 2 times 6 minus 5. In this case, what I get is, let's see, 6 minus 30 is minus 24. And then 30 minus 10 is 20. And so look at this. This actually is minus 4 times what you gave me, right? Okay, so this is telling me that A times V indeed is minus 4 times V. So I satisfy this criteria of being an eigenvector. A times the vector is equal to a number times the vector. A times V was actually just minus 4 times what you gave me. So this implies that, yes, V is an eigenvector for A, for this matrix A. And we know what the eigenvalue is. It's going to be lambda is minus 4, right? It's that number that you get scaled by. Okay, so the punchline here is that it's easy to check if something's an eigenvector. Okay. So, of course, the question now will be, how did I get these vectors? You can't just kind of guess and check every time. But let me show you that, punchline here is that easy to check if a given vector is an eigenvector. But let me show you that in fact, if I tell you an eigenvalue, you actually can also get an eigenvector. So again, let's let A be the same matrix 1, 6, 5, 2. And now what I want to do is show that lambda equals 7 is an eigenvalue. And what I want you to do is I want you to find the corresponding eigenvector. Okay? So this is a little bit different flavor now, right? I've told you that here's a number now, right? Now this person on the street gives you a number and says, show that it's an eigenvalue. So suppose, it was an eigenvalue. That meant that A times V equaled 7 times V, right, for some vector, which means that, right, if I now subtract 7V on both sides, I get 8 times V minus 7 times V is the 0 vector, right? I've just, subtracted 7V on both sides. And now what this means is, well, notice here that I've got a V times both things. So I can actually write this as something times V, A minus, now I want to put 7 here, but notice that this is a matrix. And so for this to make sense, for this part to make sense, I have to put here a matrix that does the same thing as multiplying by 7. So if you think about it, this is actually 7 times the identity matrix, and that's going to be equal to the 0 vector. And so what we're asking now is which vector, right, solves this equation. This is a matrix equation. We now want to solve for V, right? And so, again, what I have here is a matrix equation, with coefficient matrix, this kind of funny thing, A minus 7I, okay? So what I'm trying to, the punchline here is what I'm trying to get at is that we want to solve, i.e. solve the homogeneous equation, or the homogeneous system a minus 7I times the unknown thing equals 0. Okay, so let me go through all this again for this particular example. So what I'm saying here is that you've given me this matrix A, and I want to consider the eigenvalue 7. So here, we know that A minus 7I is, well, the matrix is A minus 7I, which means I put 7s down the diagonal, right? I'm taking A minus 7 times the identity. I just do this coordinate-wise, right? This is minus 6, 6, 5, minus 5. And then I want to solve the system where I augment this with the 0 vector. Okay, so the system that I want to solve is minus 6, 6, 5, minus 5, augmented with 0, 0. And, not hard to see, this reduces to reduced echelon. It looks like this. So what's the general solution here? The general solution is, if you work this out, what you get is just x2 times 1, 1, right? x2 is free, and we know that x1 equals x2. So x2 times 1, 1 is your general solution. So what this is saying is that for an eigenvector, I can take anything that's a multiple of 1, 1. So I can take v to be any multiple of 1, 1. For instance, 1, 1. I mean, you can take, we can take just 1, 1 itself. Okay, and so that's going to be an eigenvector. Okay. Now let me actually check this, right? So this is, again, something you can check. So let's check. So if I take A times 1, 1, that was, if you remember, A was 1, 6, 5, 2 times 1, 1. This is going to be, well, 7 and then 7, right? And so indeed, this implies that 1, 1 is an eigenvector with eigenvalue lambda equals 7. So again, the punchline here is that if I know that I'm given an eigenvalue, so given an eigenvalue lambda, we can find a corresponding eigenvector by the usual story, solving a system, right? So this is, again, something that reduces to just solving a system. In fact, this is a homogeneous system. Okay, and so that's the kind of first steps of eigenvectors, what they are and how you get them, assuming you know an eigenvalue. So next time we'll talk more about how you actually get your hands on some of these things. So we'll see you next time.